Hi everyone, welcome to my very first video. This video is on simple problem of quantum mechanics for finite potential well. Today I'll explain the idea how to calculate energy associated with a particle for a finite potential well in the bound state. You will have only two given things. First, the potential of the well, and next, the dimension of the well. By using these two parameters, you have to say how many bond states are possible there and what are the energy associated with the particle in all these states. Today, I'm going to explain in this detail. Though it is a simple problem, I found that a number of students are sticking with this problem in graduate level. Well, let me take a potential well of width from minus a to a, that is 2a, and is symmetric about the line x equal to 0. The depth of the potential well is v naught. Now we have a particle inside the potential well, and we are interested to find its wave functions, uh, number of energy states, and the energy associated with each states. So first of all, what I do is I separate this into three part, and I part, and I solve from the Schrodinger wave equations for its even parity and odd parity. Then after doing a simple gymnastic on the mathematics, I'll get equation 1, where eta is capital Ka, xi is small ka, where capital K and small k are given like this. And this both depends on the mass of the particle, energy of the particle. But this capital A also depends on the depth of the potential, which is V naught. And in the equation 1 on right hand side, you can see the rho. That rho is this one. Rho is this one, and it depends on the width of the potential and depth of the potential well, V naught. After a few steps of simple mathematics, for even parity, we get equation 2, and for odd parity, we can get equation 3. Up to here, the problem is simpler. Problem starts from here. Now you have to find the energy associated with the particle inside the potential well in particular energy level. If you do a few mathematics from equation 1 and value of rho small k and capital K, you will get expression for the energy like this. This shows that your energy depends only on the width of the potential well and the value of xi, this value. Width of the potential usually it is given, or that you can fix yourself how much width you are going to take. But this xi in this case is very important. As you can see here, xi is the multiplication of k with potential A. A is already known for a reality problem. You just need the value of k, and value of k completely depends on the v naught potential well. Depth of the potential well. So which potential you are going to take? It makes a problem. So it's not so easy to get its solution, to get energy directly from the formula. If you use your potential, you will get continuous energy. But the energy has quantized inside the potential well, and you will get a discrete energy levels. You will get certain energy levels. You cannot get energy in the continuous form. All energy states are not possible. You have to calculate here the possible energy states. So we have to solve this transcendental equation for xi. So what we do is we plot these equation 1, equation 2 and equation 3 to the graph, and we will find their intersection point. That intersection point is xi, and that intersection point gives xi, which we can use over here to get the value of energy, because intersection point only is the solution of these three equations, that only will valid for all these. So let me take you to the MATLAB. Here, before going to the MATLAB, I want to show you that we are interested in, oh, I'm sorry, yeah. Yeah, how can we solve this graphically? You can see this equation 1. Equation 1 is the equation of a circle with a radius rho. Uh, it's like x squared plus y squared equals to r squared, where in place of x you have eta, in place of y you have xi, and in place of r you have rho. So if you have to draw a circle on the MATLAB or on other any program, you first of all need to fix the value of r. This time for simplicity, I am going to select value of r as 7. Usually, you can get a value of r in question in real practice. Usually, if you get value of b naught, if you get value of b naught from this expression, you can see if you get value of b naught and a, easily you can find the value of rho that you have to fix in your equation before plotting. So in my plot, I'm going to use r as rho, x as eta, and y as xi. Okay, and okay, uh, I'm sorry. Okay, let me start. First of all, I'm going to fix the value of x. Value of I'm going to fix from 0 to 7 because I'm going to take the circle with radius 7. Okay. First of all, I need to plot the circle. You can see here, I am going to take r equals to 7. So I have to plot x squared plus y squared equal to 49, or y equals to root under 49 minus x squared. I'm going to plot that. What I'm going to do is, I'm sorry, what I'm going to do is y equals to, sorry, I have already done that. I just want to show you. um, it's simply like y equal to square root of, you can see is a y equal to square root of 49 minus x square. Here in between multiplication you have to give dot sign. MATLABs understand that as multiplication. Dot and multiplication gives is multiplication. Next we are going to plot equation 1. Equation 1 we plot, I'm sorry, here I did mistake. Where I did mistake is on recognized variable ta. Oh yeah, you have to write here 10. Yeah, 10x. Okay, that's fine. But remember one thing, we have supposed y xi as y, but in this case, if you write here y, that will be wrong because y you have already used in the previous equation, because uh, every y are not common between first y, I mean first equation and second equation. Only special points are common. Those points we are going to find. And next equation I plot like b equals to, Mm, I'm sorry, it's not plus cos. I'm going to change this b equals to minus x cot x. Okay, now I have plotted everything. Now I just want to plot first of all x with y, it gives me a circle. Then plot x with a, it gives first transcendental equation in plotting form. and again x plot with b. We are plotting this second b equal to minus x cot x. So when I plot this, I get this type of graph. Okay, this type of graph. Here you can see you have three curves. First curve is of red color, second is of blue color, and uh, this one is of orange alley color. You can do simple graph setting. Yeah, I have not done now. I have which I have already said here. In this side, we have plotted x. As I said before, x is Ka. In this y part, you just leave y, and here is also 7, here is also 7. It means this curve has same extension in both the axes. It means it must be the circle. So this one is circle, and this red line, it is passing through 0 and has infinite asymptote at infinity. I mean, this straight line is the asymptote. It tosses this curve at infinity. So it must be the graph of 10 x 10x, because it's going to 0. We know value of 10 0 is 0. And when this curve has infinite value, this curve has 0 value. It means it must be the graph of cot minus x cot, because cot has infinite value at 0, 180, but it has 0 value at 90 degree, where the value of 10 is infinite. So this point, this yellow curve is of cot, this red curve is of 10, and this blue curve is of circle with radius 7. You can clearly see that I have labeled like this. And now I am interested in the particular points. You can see here a number of intersection points, but trickily you have to select the points. Those points are the point of intersection, this point of intersection between curve, I mean circle, and the first transcendental equation of 10. This gives you a first state of even parity. It is your ground state. Here you can see for this intersection point you have value of x equal to 1.35. Value of x means value of Ka is 1.35. Ka is xi. Now you have xi. If you have xi from the graph, easily you can calculate energy from the formula from here. Look here. Now in this expression of energy, you can see here in this energy expression, you can just substitute the value of xi, because xi is the small Ka, which we have plotted. I'm so sorry, which we have plotted over here. This is the first energy state, or I mean ground state, which has even parity, because this is the graph of 10 which we have got in even parity. And don't be confused, this is not going to give you any solution. Actually here the y is infinite. Actually in this line y is infinite, and this is just the asymptote. Don't be confused with this straight line. Now you have next point here. I'm so sorry, it should be here. Okay, it's okay. You can anyway, you can just click over there and you will get the value of x. This is the xi a. It gives second energy state, which is the first excited state. It gives the energy of first excited state, and it has odd parity because you have got this from the odd parity solution of cot. From here, just leave this straight line. Here, this point gives the value of this is Ka. Just substitute on the energy expression. You'll get the energy of second excited state, which has even parity. This point give you odd parity. It is third excited state. Again, this point give you even parity. This is fourth excited state. In total, if your potential well V naught is given, or depth of the potential well is if given, that time you will have a fixed value of rho, I mean a fixed value of the radius of circle, and for that fixed value this time we have taken 7 as our reference. We have got 5 possible energy states, and by plotting on graph we can easily get the energy associated with each states, and we found that 3 states are with even parity and 2 states are with odd parity. So this is the technique. Now we are clear on all the questions. How many energy states are possible? And what are the energy associated with the particle in that particular energy state for the given potential? So from this graph, you just have to pick up the x coordinate of the intersection point, and you have to go to the expression of energy here. The value of x coordinate is the value of Ka, and the value of K is value of xi. That xi you just replace here. You can easily get the energy of that particular eigenstate. So I hope you are clear how to calculate energy states associated with particle in finite potential well for a given fixed value of potential energy. I mean potential depth. Thank you very much. Keep working hard.